some notes on the web page with the proof that the isomorphic group is a Lie group. Kind of an elementary by hands proof from some notes by Werner Ballmann, which you might enjoy. So in fact, one uses the same techniques to prove that, for example, that the group of affine diffeomorphisms, if you have a connection, they are a Lie group. The group of conformal diffeomorphisms are a Lie group. So all these kind of things, the fact that they are Lie group, have more or less the same kind of proof. And these notes discuss actually a very nice discussion on that. So I put on my homepage some notes why the isomorphic group is a Lie group. So notes by Werner Ballmann, they're very nice notes. But you do have to work, so it's not elementary. And solutions to the take-home. I also updated the notes on symmetric spaces. Okay, so what did we do last week? I'll remind you of two things, maybe. One was we showed that R is parallel if and only if M is locally symmetric. Another fact was that if M is locally symmetric plus simply connected, this implies symmetric. This is the second fact. And the third fact, if M is symmetric plus simply connected, then it is determined by the cogent tensor R at one point. So if I understand the geometry at one point, that determines the symmetric space. It's simply connected. So today we'll give an algebraic formulation of how one does that. Then the last thing I did was to the beginning of how one does it by defining what we call Cartan involutions. So remember the way this went was, so M is symmetric. I write it as G mod K, where G is the identity component of the isomorphic group. And K was an isotropy at some base point, P0 in the manifold. And then we let S be the symmetry at that base point P0. And then we define an automorphism from sigma to sigma, which was conjugation by the symmetry S. Right, S is an element of the isomorphic group. Not necessarily of the identity component, but this preserves the identity component. So I can regard it as an automorphism of the group G itself. And then we proved that if I let this be the fixed point set of the automorphism sigma, then K lies in between that and the identity component. So this here was my notation for a fixed point set. Okay. So this was a crucial observation for a symmetric space, that one can describe it in terms of a certain automorphism of the group G itself with this property. So today we want to prove a converse of that, that if I have an automorphism, so here of course sigma squared is the identity, right, because S was an involution itself, so conjugating with involution I get another involution. So this is an involutive automorphism. And here I look groups that are essentially the fixed point set of the automorphism. And then the manifold is G mod K. Right? So I can ask for a converse given Lie group G, given involutive automorphism. Then if I let K be the fixed point set essentially, then the quotient is a symmetric space. So for this we have to first maybe recall a little bit or talk in more detail about how to put a metric on a homogeneous space. So let's G mod H be a homogeneous space. Right now this is not symmetric, so any homogeneous space. Let's call it M also. And H is an isotropic group at a base point P0. And then we have this identification G mod H to M, which takes a coset to G times P naught, and which takes left translations to the action. So we have this dual way of looking at acting on the manifold. And then we had what we call the isotropy representation. Which says that H acts on tangent space at the point P naught. Which, remember, another way of thinking of this is the identity coset of the homogeneous space G mod H. It's another way of looking at it, which takes H into the derivative of left translation at H at the point P naught. H fixes it because it lies in isotropy. So this acts in the tangent space, preserves the inner product. Well, sorry. I'm not talking about Riemannian yet. I'm just talking about general homogeneous spaces. So it lies in general linear group. Isomorphism of the general linear group. And we can say that G mod H is effective. So one has to be a little bit careful now. Forget if I discuss this issue or not, but say there's a difference between G mod H being effective and this representation being effective. I may have mentioned this before. So if I say the homogeneous space is effective, I mean that LG is the entity if and only if G is equal to E. So everything acts on the manifold. Right? So in terms of G and H, what does this mean? Let's start with a general homogeneous space G mod H, and let N be an ineffective kernel. So the set of all G and G, subset LG is identity on G mod H. Now I claim the following observation. I claim that N is certainly normal in G, just because it's an ineffective kernel. Right, so that is clear. And in H. Of course, notice that N here, since it fixes a base point, it certainly sits inside H, fixes all points, particularly the base points. So the subgroup of H, if it's normal in G, of course, also normal in H. And I claim that N is the largest subgroup of H, which is normal in G. The largest common normal subgroup of G and H is precisely the ineffective kernel. So let's see, this is pretty easy. So certainly one direction is clear. Right, N was normal in G because it's a kernel of an action, sits inside H, was normal in G and H. So for the converse, say let L inside H be normal in G. I have to show L acts trivially. That's what it means. So let's take an L in the group L. Left translation by L on a coset GH is LGH. For this to be identity means that this must be equal to GH for all G. Right, so L lies in left translation by L lies in an ineffective kernel. If and only if this is true. Let's see, what do I have to prove? L is normal in G. Well, let's take R, L, R inverse. Let's take left translation by that. that is LR, LL, LR inverse. So what am I doing? This normal in G. So let it act on GH. So what does it do to GH? It takes it to R, L, R inverse GH. Okay. But of course, this is another element of G. L has trivia on all elements. So it's R, L, H. L lies in H, so it's RH. So oh.
You want to put the first line.
Pardon?
You want to put the first line, but the left action is identity. By an element in L.
Ah, yes, that's what I want to prove.
So if you pass that sheet
So
to the right,
I want to prove that this lies in the ineffective kernel. Okay. This is LGH.
but
It's L is normal in G. So this is G L prime H. But of course, L and L prime also lies in H. So this is GH. So it takes GH to JH for all G, which implies that this is identity. Okay, right. Okay, so that's one way to formulate effectiveness. Usually it's more convenient to not make it effective. Because I notice that if I want to, without loss of generality, I could assume it's effective. Right? You have G mod H, and N inside G is the ineffective kernel. It's normal, so I can look at G mod N. It also lies in H, so I can look at H mod N, and this one becomes effective. So I can always divide by the ineffective kernel if I want. Okay. But that's not always a good idea. So the follow thing is usually better. Namely, I say that G mod H is almost effective if N is discrete. So it has trivial Lie algebra. Right? So if N is discrete, I say it's almost effective. And this is if and only if, using the same proof as over there. The largest normal subgroup in common is common is discrete, which I can now express in terms of the Lie algebra, right? Because normal subgroups are ideals. That means that H and G have no ideal in common. Right, so this language over here, if N is the ineffective kernel, then on the Lie algebra level, the Lie algebra of N is the largest ideal that G and H have in common. Okay, so G and H have no ideal in common. So it's actually a nice simple way to express almost effectiveness on the Lie algebra level. Okay. I think I mentioned last time that this does not mean the representation is effective. It may or may not be effective. But if it's Riemannian homogeneous, it is effective. So, if GX by symmetries, then G mod H is effective. if say if G is an isometry group. Sorry, so if G is an isometry group, it acts effectively on M. What else? An example that shows that these almost effective presentations are usually better. So if I want to write CPN as a homogeneous space, well, this of course the complex line in CPN minus the origin. And on this UN plus 1 acts transitively. Right, takes any complex line to any complex line. And if I look at, say, the complex line in the first coordinate, then the stabilizer is U1, UN. So CPN is a homogeneous space in this form. It's the most natural description. Is that effective or not? So do G and H have a normal subgroup in common? Right, that's the question. What's the largest normal subgroup that they do have in common? Of course, remember, an equivalent way of saying is that which elements act trivially on complex lines, which elements in the unitary group act trivially on all complex lines. Right. So n is equal to the center of UN plus 1, which remember is Z times identity. So there's a circle inside UN plus 1, which just takes all the lines to all the lines, because it's Z times identity. Sits inside H, of course, here, diagonally, right? Diagonally inside this thing here. What's the center of this group is larger, right? It's U1 lies in the center, and there's another diagonal one here. So center is two-dimensional here. But only this here is common with the center of G. So this circle is the largest common subgroup. So this is not...
In the isotropic group, wouldn't M be U1?
No. What's the isotropic group here? What's H? So it's like this, right? So the center, the circle here, is like diagonally inside U1, UN. Right? So that's important. So it's not effective. First, for example, I can take a subgroup with a special unitary group. It also acts transitively. And what's a stabilizer? Again, matrices of the same form. But now I have to require that the determinant of the whole matrix is equal to 1. So this times this, its determinant must be 1. So we denoted it in this form. What's the ineffective kernel in this case? Right, so whatever sits inside here has determinant 1. So that's the nth root of unity, diagonal Zn. So it's almost effective, right? So this is almost effective. To make it effective, I get a really ugly description. That's the effective version. So that's usually not how you want to work with, if you want to do computation in CPN. It's not very convenient to work in this quotient group here. This is very nice. In fact, for in the cases where the group G is UN, so when G is equal to UN, it's often convenient to at least let the center act in effectively. So this description looks very nice and simple. But this is just the diagonal ones. So computation and this description are very nice. It's not effective, but it usually doesn't matter. But certainly in many cases, we're going to write things as an ineffective homogeneous space. For example, even if I look at M equals SO2n mod UN, nice simple homogeneous space. What's the ineffective kernel in this case? So what normal subgroup do they have in common? So remember another fact. If I suspect the space is almost homogeneous, what does that mean? Where does the ineffective kernel have to, the discrete ineffective kernel have to lie? Must be a subgroup of something that we know. It's discrete and normal. There was a fact we talked about the first couple of weeks. It must lie in the center. Right? So there was a general fact we had a discrete normal subgroup of G connected is contained in the center of G. Ineffective kernel is a discrete normal subgroup. It's almost effective. Must lie in the center. So all I have to do is test the center. I look at the center of G, and the question is, does it lie in H? Because the ineffective kernel is the largest normal subgroup that G and H have in common. So center of SO2n is plus minus identity. Does it lie in UN? Sure. Minus identity is complex linear. So it's not effective. N is Z2. The center of SO2n. So I'd have to also divide by Z2 to make this into an effective homogeneous space. Clearly not very convenient. Okay, that's one issue. Next issue is I want to compute the isotropic representation. For this, it's convenient to identify the tangent space with something else. So first, a general fact about vector fields. Say G acts on M. Doesn't have to be homogeneous now. This is a general fact about group actions. If I take an element in the Lie algebra, I can interpret this as a vector field on M. Right? G acts on M. Element in the Lie algebra has flow given by left translation. It acts on the manifold. That defines a vector field. It's often convenient to distinguish the two things, to say that X lies in G and have a vector field on the manifold. We call this X star. They're often called action fields because they come from the action. So what is that? If I want to compute X star at a point P, well, I look at the flow of X. That's given by exponential map. Right, so X Tx, that's the flow of X on the group G itself. Let it act on the manifold, and then differentiate. So d dt at t equal to 0 of X Tx times P. So it gives me a well-defined vector field on the manifold, and that's, if I need to be careful in the distinction, that's how I go from X to X star. I can now use this to identify, well, maybe not yet. But we want to compute this. This is our goal. For this, it's convenient to look at the following thing that's called a reductive decomposition. of G. So something of the form G is equal to H plus some complement, I want to call P. So it's just now a vector space direct sum, right, such that at H takes P to P. Because in particular it means that on the Lie algebra level, heap vectors between H and P must be contained in P. But it's a little bit stronger because H may not be connected. So reductive decomposition of a homogeneous space, right, is a decomposition of the Lie algebra level which has this property. And now I can use this to identify with the tangent space of the manifold at the base point P naught by taking a vector x in P and sending it to the action field at the point P naught. We define it over there. That's natural identification of the manifold with something inside the Lie algebra. And we want to do Lie algebra computation, so that's what we want. So using that, I have the following proposition. If I identify in this fashion P with the tangent space, then left translation by an element G as a, derivative of LH at the point P naught corresponds to at H as an element that goes from P to P. Right, this here goes from TP naught to TP naught. And over there it goes from P to P. Identify P with TP and by this kind of map over here. So I can compute the isotope representation just in terms of the adjoint. And we know how to compute adjoints. So this makes the object very, very computable. Some other properties we can collect at the same time. Slightly more general, which will be useful. If sigma is an element in out G, so here, of course, implicit is also that M is G mod H. If sigma lies in out G, and sigma of H is equal to H, then sigma induces a diffeomorphism from G mod H to G mod H, which takes a coset GH into sigma of G times H. That's well defined because this takes H to H. Right? If I modify G with an element in H, I put that right here, that's the same thing. And the conclusion is, so this implies that the derivative of sigma bar at the point P naught is the derivative of sigma restricted to P. Right. D sigma takes the Lie algebra to the Lie algebra, Lie algebra G to Lie algebra G, are restricted to the subspace P. And under simplification again, so under simplification here, if I want to write like this, they become the same. As we're going to see, B easily implies A, but it's useful to have this more general version. And then using that, we can now also prove the following, that if G acts by isometries on G mod H, then the metric on P naught is equivalent to a metric on P invariant under at H, which preserves P because I have a reductive decomposition. Did I mention that? So here, our setup was M is G mod H, and I have this inductive decomposition. Then I use identification, and then A and B hold. And in C, I put the metric on P, again by using this identification. I have a metric here, I can pull it back here. It then becomes invariant under at H. Of course, C is immediate because of this property here, right? So if I pull back the metric from here to here, here the isotrope acts by isometries by definition. Then here it becomes at H, so at must act by isometries. Then the converse holds. If, say, I have an inner product on P, invariant under at H, this defines uniquely a metric on G mod H, invariant under G. Okay. So all these are easy, I claim. I'm going to start with part B. So this right here. So what do I have to prove? This identification is x goes to x star. Right? And this was ddt of x tx times my base point p naught at 0. So what's that supposed to mean? Sigma acts on P. So I take d sigma, apply to x lies on P. And this is what the right-hand side means. And d sigma bar is a diffeomorphism from G mod H to Z mod H. That's my manifold. I can apply it to an action field. So I have to show that's equal to d sigma bar applied to x star at the point P naught. That's what that relationship here means. And the identification here is x, here's x star, and then they should be the same. Okay. So let's maybe start with this one right here. What is this? It's d sigma bar applied to ddt of x tx times p naught. Right, so that is, use a chain rule, ddt of sigma bar applied to x tx times p naught. And what was that? The sigma bar just acts on the cosine like this. So it becomes ddt of sigma of x tx times p naught. That's now in the group. And now I can use our properties of automorphism. That's the same thing as x of t d sigma applied to x. And automorphism is not compatible with the exponential. And this becomes what? It becomes d sigma applied to x star at the point p naught. Right, so here's my vector. I go in this one parameter group, back to the point, differentiate. That's an action field. So in fact, maybe this here wasn't quite what I want to prove. I have to use it, claim that user identification. But what does that mean? It means that this star at the point p naught is equal to this. Now they lie on the same side in the tangent space of M. Right, so that's what it means to be precise. Okay, that's the proof. A now follows easily. I simply use B by letting sigma be adjoint of H, where H lies in H. I want to show that at H is the same thing as the dot LH is the same thing as at H. So this here becomes d sigma bar. Right? This becomes d sigma. So that's d sigma bar, this notation over there. And d sigma is simply at H. Sorry, conjugation by H. And then d sigma is at H. How does conjugation by H act on G mod H? So it takes GH to GH, sorry, to HGH inverse, that's conjugation, act on the course at H. But H lies in the group H, so that's the same thing as HGH. And that's the same thing as left translation by H. Okay, so I regard left translation by H on a homogeneous space, I can regard as induced by conjugation by H. So this becomes conjugation, differentiate, and this becomes at H, and that's what I want to know. Okay, so we always use that application between P and TPM, and the isotropy is at H. C is now obvious, like I said, right? Isotropy, X bar symmetries, therefore at H X bar symmetries. And D is something we may have discussed before also. Right? I have an inner product on P. Let me write it down again. So this inner product on P, which identify with the tangent space at P naught. Here it's at H invariant. Here it's invariant under the left translations. And then I define the metric at any other point on the manifold by using left translations. At the identity, I guess. So take your vector, go back to the point P naught with left translation, take the inner product there, and then you have inner product at the point in the manifold, and now you show it's independent of the choice by using the fact that this inner product is invariant under left translations. So check independent of choice. So I won't do this now. I think we've done it before. Okay. Notice in particular, this means now that you can describe the set of all G invariant Riemannian matrices in a homogeneous space. Becomes finite dimensional. So I look at the space of G invariant metrics on G mod H is identified with a cone in the vector space of symmetric bilinear forms on P invariant under at H. Right. So here I have a symmetric, inner product is a symmetric bilinear form, certainly. It must be invariant under at H. Right. This becomes a vector space. But now I have additional condition, it must be an inner product, must be positive definite. That makes it into a cone inside this vector space. Particularly it's finite dimensional. And in fact, if one uses some representation theory, one can even describe the set of all possible inner products, which I don't want to do right now. Okay. Well, for example, say if G mod H is what's called isotropic reducible, so i.e. at H acts irreducibly on P or on TP naught M. This implies that the metric is unique up to a multiple. Right? Remember, if I have two inner products invariant under an irreducible representation, they are about each other. And then by the same argument we discussed earlier, the metric is Einstein. So in other words, Ricci of the metric is a multiple of the metric. Okay. So these kind of isotropy reduced homogeneous spaces are quite interesting. Some are symmetric space, but there are many others. So they're kind of Einstein by definition, if you want to. Okay. Maybe one more comment. If G acts by isometries on G mod H, so it's called a Riemannian homogeneous space, then I claim then there exists a reductive decomposition. So how would I do that? So I have G is H plus, sorry, I have H sits inside the orthogonal group of the tangent space at P naught. In fact, there's an injective embedding given by the isotope representation. And as you said, because it's Riemann homogeneous, that's effective. Notice that it doesn't quite imply H is compact, but at least it has compact closure inside here. So this implies that H closed is compact. So then I can do the following. There exists, this implies that there exists a metric on TP naught M, which I identify, oh, I don't identify, on TP naught M. Sorry. There exists I want to claim there exists a metric on G, on inner product on G, invariant under at H, acting from G to G now, not just from P to P. We don't have a P yet, we only define a P, reductive decomposition. H, if it's compact, those will be obvious, right? Take any product, inner product on G and average over the group H. If it only has compact closure, how do I put a metric on G? I'm going to do the following. G sits inside the isometry group of my Riemannian manifold M. M is G mod H. And the isotopy of I of M at the point P naught is compact. And of course, H sits inside the isotopy. And G sits inside the Lie algebra of the isometry group. So now I claim there exists an inner product on the Lie algebra of the isomorphic group invariant under its stabilizer. Because now the stabilizer is compact. So the average, take any inner part in this Lie algebra, average over this bigger stabilizer. Now it becomes invariant under at, now restricts to G. And this is then invariant under at H, because H is smaller than the stabilizer of its full isomorphic group. So there's an easy way to get around to this technical point that H in here may not be closed. So once I have that, then we want to define P. Now I can just choose as P the orthogonal complement of H with respect to this invariant at H invariant inner product. Because this now implies that at H takes P to P because at H acts by symmetries. So it preserves H because that's the Lie algebra of H. So every Riemannian homogeneous space has a reductive decomposition. So you might as well assume it. And in this theorem that I just erased, the way we described the inner products was in terms of some reductive decomposition of the Lie algebra. But they always exist if it's Riemannian homogeneous, so no restriction. Example and exercise that if I look at a space as a homogeneous space, I claim in this case there exists no reductive decomposition. And the isotropy rep is not effective. I believe it has a large ineffective kernel. So this has no Riemannian metric on it with this X bar isometries. So it is a condition, but we're going to study Riemannian homogeneous spaces, so we don't have to worry about it. What else? Maybe one other remark, which is connected with this problem right here. So if G mod H is Riemannian homogeneous, and the following thing is true, then H inside the orthogonal group of the tangent space is closed, means compact, if and only if G inside the full isomorphic group is closed. So that it's the property on H, the same thing as the property on G. And that's an exercise. That's not hard. But this means that you might as well assume it's closed. Because I could always take the group G inside the isomorphic group. Is that closed? I could take the compact closure. Right, so if a metric is invariant under G, on M is equal to G mod H, then it's also invariant under G bar. And then I can write M as G bar mod H bar by G is transitive, so the bigger group also is transitive, has a certain stabilizer, and this is compact. You might as well assume, whenever you talk about Riemannian homogeneous spaces, it's of the form G mod H with H compact. That's convenient. And then I write down an effect in a reductive decomposition in the fashion that I discussed here. Okay, so it's all background. Now we can prove the converse of... no, before I do that... let's observe that for a symmetric space, exists a natural reductive decomposition. So let's recall our setup. G is the identity component of the symmetry group. We assume that's symmetric. So then I think I wrote them as K. Maybe to keep a distinction a little bit for a while. For the symmetry space, I write the stabilizer as K. For a general homogeneous space, I write as H. Just a convenient way to remind us. Symmetric space. And then K was contained in the stabilizer of an automorphism. So K was a stabilizer at my base point P naught. And then I conjugate with the symmetry at P naught. This was an automorphism of G. Involved automorphism of G, and then K was in between. So this was what we proved last week. In the setup now, I have a natural reductive decomposition. So let H and P be the +1 and -1 eigenspace of d sigma, which goes from G to G. Right, sigma was an involved automorphism, so d sigma is as well. So d sigma squares the identity, so there's a +1 -1 eigenspace, and the whole thing decomposes into its +1 -1 eigenspace. So right now, forget about the isotropic group K here, although it's going to be the same. Maybe I should call it K then. So then K is the Lie algebra of K. So what do you expect? So certainly K, K is contained in K. But now also K, P is contained in P. And that's our definition of reductive decomposition. Right? I have G is the sum of K and P. Reductive meant that Kp lies in P. While a little bit stronger it was, so and at K takes P to P. It's a little bit stronger because K may not be connected. In addition, I have one more property, namely P, P sits inside K. And that's a very strong condition. So this condition is very strong. And so that's what I mean by the natural reductive decomposition of a symmetric space. So the symmetric space gives this automorphism, and you let the decomposition be the +1 and -1 eigenspace of d sigma. Well, proof is very simple. What does this say? It says that K and sigma have the same Lie algebra. And the Lie algebra of G sigma is a set of all vectors x and g, which are fixed by d sigma. And so again, we easily prove that by using the exponential map in our usual fashion. And that's what we call K. So indeed, the Lie algebra of capital K is little k. So we might as well keep the same letter. And these relationships just follow because d sigma is an automorphism. Right? So d sigma an automorphism implies the Lie bracket relationships. plus 1 eigenspace goes to plus 1 eigenspace because it's an automorphism. Minus 1, bracket with minus 1 goes to plus 1 eigenspace, so it lies in K. Minus 1 plus 1 eigenspace becomes a minus 1 eigenspace, so it lies in P. This property is a little bit stronger, so you have to think about why this is true, but these are all clear. This by itself here, this means a reductive decomposition. Let's call it Cartan decomposition of the symmetric space. Whereas this is a property that tells me it's a symmetric space. So again, this is a crucial property that's very strong. I still want to see this one here. So let's take an element in K. I want to look at K applied to X, where X is an element in P. And how is P characterized? It's the minus eigenspace of d sigma. So I have to show that this lies in the minus 1 eigenspace of d sigma. But sigma is an automorphism. So what is this? I claim it's at sigma of H composed with d sigma applied to X. So why is that? So on the group level, what is this? At K was is a derivative of the left translation. After all, was the isotropy, right? So what is that? I think it's L sigma H composed with sigma. Right, so let's apply this to GH. This sends it to HGH. Sigma sends it to sigma of HGH, which is sigma of H, sigma of GH. That's left translation by sigma of H, applied to sigma GH, and that's L sigma H composed with sigma. Okay. Of course, to be more precise, this is really sigma bar, right? The induced automorphism on the symmetric space. Now differentiate. I use that sigma H is equal to H. H was a fixed point set, so it becomes equal to H. And d sigma X is minus X, so it becomes minus at H applied to X. So X was in the minus 1 eigenspace, so again, this lies in that minus 1 eigenspace. Okay, so this property is also true, even when K is not connected. Because if K is connected, this and this will be the same thing. Okay. Now notice that this setup, I can do it in the right order. Yeah, okay. So now I can construct the metric. So G is connected. Sigma is an automorphism. It's volative. And for any K inside G with K lying inside the stabilizer and containing the identity component. Such that K is compact. Any K in G with this property, any G invariant metric on G mod K is symmetric. And of course, we already saw, because K is compact, G mod K has a G invariant metric. It doesn't matter which one I choose, any such metric must be symmetric automatically. So all I need is a setup. Right? So now we have the converse of what we did last week, Wednesday. Any involved automorphism, look at its fixed point set. I do have this additional condition that K must be compact in order to get any metric on it. So that's, for example, I certainly need that the involutive automorphism has a property that its fixed point subgroup must have compact identity component in order for any K to exist, which is compact. Okay. So I can't choose any involutive automorphism. It's a little bit stronger property. But certainly now I have a kind of one-to-one correspondence between something geometric and something algebraic. So this now is completely algebraic. And the proof is very simple. So let G is equal to K plus P be the Cartan decomposition. Of d sigma plus and minus one eigenspace. And let this be any metric, any metric on G mod K invariant under G, which remember is in one-to-one correspondence with a metric on P invariant under at H, under at K, what we just discussed in general for homogeneous space. Now I have to show that symmetric. So I have to find a symmetry at P naught, pins at any P, because it's homogeneous. So I find a symmetry at one point, I find a symmetry everywhere. And what should be the symmetry at the point P naught? Well, what could it be? It should be given by the automorphism. So I claim sigma bar as a map from G mod K to G mod K is a symmetry at P naught. So remember how it acts. It takes GK to sigma GK. So it certainly fixes P naught because sigma is an entity of K. Sigma fixes everything in K. And what's d sigma bar at the point P naught? Well, that's in one-to-one correspondence with at d sigma restricted to the reductive component P. Right, on the left-hand side, this was part, I think, B in the theorem. Sigma was an automorphism. Sigma bar is induced automorphism on the manifold. And d sigma bar is d sigma, but now restricted to P. Of course, d sigma restricted to P is by definition minus identity. Okay, so that's what I want for symmetry. And sigma bar is an isometry since certain d sigma at the point P naught is. So it's an isometry at one point Now I want to say it's isomorphic at all points. So what do I have to use? This right here. So and sigma bar composed with LG, now for any G, is L sigma G composed with sigma bar. Right, so now take the derivative identity. Then I get the derivative of sigma bar at G composed with the derivative of LG at identity. Its derivative with left translation by sigma G at the identity composed with d sigma bar at the identity. No, that's isometry. Left translations are by definition of isometries. Therefore, that's an isometry. And by definition, it's derivative minus identity at the point. So it's a symmetry at the point. Okay. And then I get a symmetry everywhere. So notice here I didn't have to use what metric I choose. It doesn't matter as long as it's G invariant. Okay. I use this K invariant right here to say it fixes the point P0. That's why I use its K invariant. That's all I'm using. Okay. I can reduce this a little bit further. Make it completely infinitesimal. So let sigma be a Lie algebra. A an automorphism of the Lie algebra. We square the entity. G is K plus P plus or minus one eigenspace decomposition. So then I have, as before, that K comma K sits inside K. K comma P sits inside P. And P comma P sits inside K. And if G is the unique simply connected Lie group is Lie algebra G. And K contained in G, the subgroup, is Lie algebra K, which it is because of this relationship right here. Because all I'm assuming is invariant automorphism. That's all I'm assuming, right? This will be a consequence. Then I can choose G and K in unique fashion. And then the claim is then G mod K is a symmetric space. So now I have a completely Lie algebra description of a symmetric space. Well, there's one thing missing. That's not quite true. What else do I need? I just erased it. I needed that K is compact. Then, if K is compact, G mod K is a symmetric space. And what do I need to prove this? That's precisely the previous theorem. So all I have to observe that this certainly implies this. Again, because A is an automorphism. preserves eigenspace like this. So this relationship is a consequence. K is a subgroup that defines G, defines K. I get a homogeneous space G mod K. This is a reductive decomposition. K is compact by my additional assumption. And now every G in variometric, in fact, is symmetric. Okay, so that's immediately follows from the previous one. So again, these decompositions with this property, they're called Cartan decompositions. And then it's called orthogonal. So if I say an orthogonal Cartan decomposition, is if the group K is compact. This is my Lie algebra definition. That's a Cartan decomposition. Orthogonal means K is compact. And effective means G and K have no ideals in common, which remember means that G mod K is almost effective. So that means putting everything together, there's a one-to-one correspondence between G mod K symmetric plus simply connected and orthogonal effective Cartan decompositions. Of Lie algebras, of any Lie algebra G. So why did I add simply connected here? So first notice that in this setup here, I actually it's a consequence. It's a simply connected symmetric space if I want to. I can add that. Why is that? Well, let's remember we have, how do I just cite such things? I have a vibration from G mod K to G mod K. Then I have a long homotopy sequence. That's an exact sequence. And I'll prove over there G is simply connected, so this one here is 0. K is connected, this one is 0. So therefore this one's equal to 0 also. So in this direction, when I go from this pure Lie algebra setup to the corresponding manifold, the manifold by construction is simply connected. And of course, if I want to go from the manifold to the Lie algebra level here, I'm not going to see any coverings. If I throw this away, I get coverings. So I might as well throw this in here. Then I get a one-to-one correspondence. But a word of caution. So it's not completely a one-to-one correspondence because of the following example. So let's look at Rn with a flat metric. This example I've already discussed several times before. It's always an exception. This is a Thorn group, cross translations. So let's call TV, B's and Rn. Then I claim I can do the following. First, that's a symmetric space, right? What's the involution? Sigma of say, a pair A, a rotation in the translation, should be equal to what? So we need a symmetry that defines a corresponding symmetric space. So what is it supposed to do to A? So what's ON here? That's the stabilizer of the origin. Symmetry is supposed to fix the stabilizer. What should it do with the translation? It has to change, of course. So T of minus B. So this will be the complement, right? So if I look at my Lie algebra here, I split it into skew symmetric matrices and the vectors V. Here it's identity, it's minus identity. That's my Cartan decomposition. On the other hand, I can now do the following. If K inside ON is any subgroup, then I can also write Rn as K cross translations divided by K. And notice that sigma of K takes K to K, because sigma on ON is the entity. So sigma is also a Cartan involution of this description of the Euclidean space. In other words, on the left-hand side here, I have infinitely many ways of writing Rn in terms of Cartan involution. Of course, they're silly in a way. But nevertheless, that correspondence is not completely one-to-one. On the Lie algebra level, I always see, on the Lie algebra, I get different Lie algebras. Of course, Lie algebra G here, this will be my G. It's different for different Ks. So for different Ks over here on the right-hand side, I get the same manifold, Rn. It's not completely one-to-one, and we're going to see that this is the only exception in the sense that it's not one-to-one. So if I split off flat factors, these kind of things here, then this is going to be a one-to-one correspondence. And that we'll be able to see prove next week. Another issue that we're going to have to face then is if I start with G with an involution sigma and then write down G mod K, the symmetric space the way we did it today, it's not clear that G is the anti-component of the isometry group, as it usually is when we start with a symmetric space. Right? We take this group, it's transitive, we define a Cartan involution there, we get our setup in terms of this group. But if I do it the other way around, if I start with a G in automorphism G mod K, then that G may not be the full isometry group. Again, an issue in which it's hard to understand the one-to-one correspondence, because there might be different Gs giving rise to the same symmetric space again. And we're going to see that if I split off Euclidean factor, the factor is the same. So in Euclidean factor, you see that indeed this is not the full isometry group, it's anything in between the full one and just the translations. Okay. But this is only a problem for N. I'm going to be able to show that. Otherwise, we get a really nice, very nice, simple one-to-one correspondence. So now the whole problem of understanding or classifying symmetric space becomes a Lie algebra problem. Okay, on Wednesday I'm going to do lots of examples. I'm going to describe to you all examples of symmetric spaces where the group G is a classical Lie group. You can write them all down, and they're very beautiful. And I'll discuss them on Wednesday. Luckily, when you do this, the subgroup K is never exceptional. It's always also a classical Lie group. There's no a priori reason for that. If it was exceptional, I would have a harder time describing it, since we haven't discussed all exceptional Lie groups yet, except for G2. If G is classical, K happens to be classical. I don't know any a priori reason. The symmetric spaces are classified. If you look at the list, you can observe G classical implies K classical. I'm going to describe all those symmetric spaces on Wednesday. And remember, all I have to do is find these involutions. That's all I have to do. It's actually very simple to make something into a symmetric space. All I have to do is describe the involution, then I'm done. Okay. please pick up your exam. I think I mentioned on my homepage are solutions to the exam. I updated the symmetry space notes, and they also